today's video, I'm going to show you how I implemented Natural Language Query, or NLQ, to pull in relevant product data for our fully conversational e-commerce chatbot. Compared to semantic search, this NLQ method dramatically improved the accuracy and relevance of product results in response to users' queries. You can see this here, where in response to the same question, this NLQ approach was significantly more accurate than the previous semantic search version. If you're looking to implement NLQ in your chatbot or AI system, then stick around, as I'm going to walk through step by step how this can be achieved and things to look out for. Links to the various resources are in the description below. I've also shared the chatbot template if you'd like to try this out for yourself. Let's get started. Firstly, what is Natural Language Query? It's exactly what it sounds like. It's creating a query, in this case an SQL query, using natural language. Here's how it works in our chatbot. When a user sends a message, it, along with a conversation transcript, is sent to a large language model, in this case GPT-4o. The LLM reflects on the message in the context of the conversation and generates an appropriate SQL query if the latest user question is related to products. This reflection is important as it can help maintain the context of the conversation. For example, if a user asks a follow-up question, what size does it come in? Then the LLM can look into the conversation transcript to figure out what product that's in reference to. This SQL query is then executed against our database, and the relevant product results are returned to the chatbot for processing and rendering to the user. So why natural language query instead of semantic search for a chatbot? Both methods have their strengths and weaknesses, so it really depends on the type of data and the use case that you have. Understanding their differences will help you decide what's best for your specific use case. In our first video of the series, which you can watch here, we used a vector database for semantic search across our product catalog. Semantic search uses vector embeddings to understand the meaning of the product catalog and also the meaning of the user query. While this approach worked well for certain types of queries, we found it had limitation when it came to retrieving products. In that video, I asked the question, what lycra tops do you sell for men? The semantic search engine using vector embeddings returned 15 results, of which only one was actually a lycra top for men. And that was in the middle of the 15, so it was not prioritized at the top of the list. So the semantic search engine and the embeddings LLM didn't grasp the classifications of the product catalog, and instead was interpreting the query based on relevance as opposed to precision, which is what you would expect from a semantic search engine. With so many irrelevant results being returned from the search engine, I needed to implement a performance-heavy filtering mechanism, which unfortunately just couldn't scale. The quality of the results could definitely be improved by changing the embedding LLM or fine-tuning the model, but I wanted to try out Natural Language Query as an alternative. Natural Language Query works well if you have a simple, well-structured dataset. If your dataset is highly relational with lots of tables and joins, it may be difficult for the LLM to generate an accurate query first time. In this case, you may need to generate indexes and use that as the basis for the retrieval. A disadvantage of using Natural Language Query instead of semantic search is that NLQ misses the semantic nuances of the user's questions. So if users are searching for products using terms that aren't specifically mentioned in the product dataset, it's not going to return results. Before we jump into the chatbot flow, I wanted to say, if you find this video helpful, please hit the like button, subscribe to our channel for more AI chatbot content, and if you have any thoughts or questions, drop them in the comment below. Okay, let's take a closer look at the new flow of our chatbot system. So here's a high-level overview. The chat starts, a welcome message is shown, and then the user enters the query. From there, it goes to a message manager, which makes some key decisions based on the query. This is an LLM call that I'll show you in a couple of minutes. From there, the first decision that's made is this query reasonable in the context of it being an e-commerce chatbot? LLMs can obviously answer all types of queries, but because this chatbot is specific to a business, we want to make sure it's only answering questions that are relevant. So within this reasonableness check, if it's reasonable, it can pass to the next stage, whereas if it's not, it's kicked back and a fallback response is created and returned to the user. So the next decision is the knowledge base needed to answer this query? As I mentioned, in our first video, we used semantic search for all company knowledge. That included products, categories, static content like customer service, FAQs, refund policies, shipping policies, etc. Semantic search works very well for unstructured data like those types of policies and FAQs. So we want to keep that semantic search, but instead we want to decouple the product catalog from that. So if the user's question can be answered by something contained in this knowledge base, then we want to fetch that data and drop that into the context of the generation. If not, we can skip to the next stage. So the next decision then is, Are products needed to answer this user's question? If yes, we can go and generate and trigger a natural language query on the product catalog. If not, we can just generate a response back to the user. So in scenarios where products are needed to answer the query, we generate that query via an LLM call, and I'll show you the full details of that. And then once generated, we pass it into our database to retrieve the results. In this scenario, we're using Supabase for a remote database. If no results are found, we then generate an output to the user reflecting that. Whereas if there are results found, it then goes to a processing stage where we do a final check to make sure everything that's been returned is relevant. And we set up our product carousels and product cards to show the user as part of the user interface. And then we generate the output and it's back to the user and the cycle starts again. So while this flow is quite sequential, it does have agentic features, that the ability to make decisions and then carry out actions off those decisions. There are lots of reliability issues when deploying autonomous agents. So actually by deploying sequential agents like this, it's possible to get much better reliability and accuracy in a production context. Here's a quick look at the dummy e-commerce store that we set up for this series. With this, we're using Magento Community, and this installation has sample data, which contains over 200 products, along with 12 different support articles from customer service, FAQs, and the various policies of the store. In the first video, we did quite a bit of work in extracting out all of the product catalog from this installation. So here's a quick look at what we're going to be importing into our database. This covers everything from product name, categorization, descriptions, pricing, stock, image URLs, more info, sizes, colors, etc. To be able to query a database remotely using REST API endpoints, I used Supabase. Supabase is a database as a service style platform, and it's very easy to get started, create a database, import data, and then access it via API. So within a few minutes, I was able to create an account, log in, create the table schema, and then import content into that table. As well as REST API endpoints, Supabase comes with various client libraries, so it's very easy to install it in whatever framework you use. So then to test out the REST API endpoints for this database, I used Postman, which is a great application to quickly trigger APIs. And here it is set up. I'm hitting this function, execute query, which was defined in Supabase. And all this function does is it accepts an SQL query and then triggers it on the database. With various authentication headers set, you can then just pass in an SQL query and then it spits out the result. So as you can see, this is all coming from the Supabase database. So the idea here with natural language query is that the LLM is going to generate the query that we're going to inject into this API call. That should then return the relevant results based off the user's question. At the end of the video, I'll talk about considerations when implementing a system like this, particularly from a security and a permissions perspective. So the next stage is we need to get the LLM to generate a query. Before doing this in the chatbot builder, let's test it out on OpenAI's Playground. What's great about using the Playground for this is that you can set the system message. You don't have this level of access on ChatGPT. When we're programmatically triggering these LLM calls in our chatbot builder, we will be setting quite sophisticated system messages. So by being able to set it here, we can very easily replicate the types of response we're going to be getting from the API. All right, so here's our system message to generate the SQL query. Here we're saying that the bot is a sales assistant, customer support bot, and an expert Postgres SQL query writer. And we're describing that they're in the middle of a conversation with the customer. They need to review the latest message, but also put it into the context of the thread of conversation. And then based on this, write an SQL query to query the product table. And then it provided specific instructions on the types of questions that it's going to receive from users and how to handle those when generating the query. This covers broad product searches, narrow product searches, and individual product searches. From there then, I detail the table structure. This is the best way to describe to the LLM how this data is structured. It's an actual create table command. Then I also provide an example record of the data. And finally, I give examples of the types of data in the various fields. This is to try to get the LLM to align the query to the data that's in the database. So you can see I go into detail here on the categorization structure, types of attribute values for product colors, attribute values for product sizes, etc. And then finally, only output valid Postgres SQL on a single line with no other text. I also do say to limit the results to 5 here. That being said, it's worth enforcing that at the server side. Okay, let's test this out. What lycra tops do you sell for men? And then run. And then you can see the SQL query that comes back. So select all from Luma table, where categorization is like men's/tops. And title is like lycra, or description or product more info is like lycra. So if lycra is mentioned anywhere and it's in that category, then it's going to return results. So next stage is let's test this out against the API. So I'll copy this out, bring it into Postman, and then send it. And as you can see, we have 1, 2, 3, 4, 5 back. As you can see, Lycra is mentioned there. Lycra is mentioned here. That's a men's top, and Lycra is mentioned also. As you saw in the flow diagram, there is an additional filtering stage after the results are passed back from the database to the chatbot before the response is rendered to the user. This is a sanity check just to make sure the results are relevant. And there's a good example here as to why. So here we're looking at all data from the Luma table where the categorization is like men's tops because the query was, I want to see what tops are available for men that have Lycra. The problem here is this fifth result, the categorization is women's tops, but actually it has men-tops, which is why it's returned. So it is still necessary to provide some level of filtering after the results come back, just as a final sanity check. But that being said, I have found the results from this natural language query to be a lot better than what were coming back from the vector database. Great, so let's integrate it now into our chatbot system. So our chatbot is built using BotPress. As I mentioned, I'll include a link to this template in the description below. BotPress is a low-code platform. So once logged in, you have a full Visual Studio to build out your conversational flows. So you'll see the various nodes and cards here represent everything that I have in this diagram. So to go through it step by step, conversation is started, welcome message shown, and then the user provides an input. We reset some variables, and then first step is the message manager, and the message manager is making some key decisions then, as we talked about. So then off the back of those decisions, which are saved to a variable, we're able to work through the flow. So if the message is not relevant, we kick it back. If the message is relevant, do we need information from the knowledge base? And if so, we fetch that knowledge up here. We then go to the third stage where the question is, do we need products to answer this query? And if so, we then create the SQL query to be passed to the database. So what you saw in the OpenAI playground is essentially here. From there, that query is written to this variable, and then we have some custom code which passes that query to the Supabase REST API with the results being saved. If there are no results from the database, we then follow this flow where we generate an output off the back of there being no relevant products. Where if there are products, we then go through an additional LLM call. So here we're carrying out a final relevancy check, and then we're also getting it to build out the product carousel. And there's also some custom code here to complete that task. And finally, we generate the message to the user, print it in the user interface, and then we're back to the start of the flow awaiting the next message. Okay, let's test this out. We're going to use the same Lycra tops example that we used earlier. So let's go to men's. Let's just see what's in the category first. So men's, tops, material, Lycra. And this way we're going to be able to evaluate the response that we get. So there are three options here. So let's open up our bot, which is now published. And we'll ask it, do you sell Lycra tops for men? So here's the response. Yes, we do sell Lycra tops for men. Here are the options. So Helios Evercool is correct. Slightly different version of the t-shirt color, but that's fine. Tristan Endurance is fine. Again, a different color. Price is correct. Yeah, interesting. So Cassius Sparring Tank they're showing, and not the Taurus. So let's have a look and see what's going on behind the scenes. Okay, so I've rerun this query in the emulator in BotPress, and I'm getting the same results. But when I look then at the product list, interestingly, it is actually returning this Taurus Elements shell. But then as part of that relevancy filter after the results return, it's actually deeming it that it's not relevant because it's a jacket, not a top. So that's interesting. That may be correct, may not be correct. And then also it is picking up this other product. So let's have a look at it. This Cassius Sparring Tank. Yeah, so this is 4% Lycra. So that's interesting. This product doesn't actually have the Lycra attribute associated with it. So it's not showing in this filter result, but the product actually is a Lycra product. So arguably this is returning better results than actually what is appearing here on the shop. It has included this product, which arguably should be in this category. And actually the definition of what is a top is up for debate. So GPT-4o deems that this product isn't a top because it's a jacket, whereas on this website, jackets are deemed to be a top. So that could be ironed out in terms of more specific prompts around the definition of the category structure. But generally speaking, these are very good results. So let's carry out some more tests. Let's try a really broad question. What rucksacks do you have? This is an interesting response. The SQL query most likely returns 0 results because the word rucksack doesn't appear in the dataset. If I go to gear and bags here, you can see that there's plenty of backpacks, just the word rucksack is most likely not mentioned. So this gets back to the issue about how natural language query loses the benefit of semantic search, but it actually gains it in terms of precision on terms that are in the dataset. So ways to get around that might be to have an additional column in the dataset, which can be synonyms, and that could contain the word rucksack against these various product lines. or maybe by playing with the prompt generation to get it to inject additional synonyms to try to reflect back a better result set. So just to confirm this, let's ask the next question. What backpacks do you have? And as you can see, it is now correctly retrieving the various backpacks that are on sale. So let's try a more narrow product search. What men's pants do you offer that are suitable for yoga? Okay, so here's our response. Great selection of pants for yoga. And we have 1, 2, 3, 4. So let's check it out. We don't actually have a yoga filter. I've just searched and we have 1, 2, there's 3 showing there. So the Zeppelin is there. Livingston is this one. Let's go into that in a minute. Orsted is there. And Cronus. So yeah, good results. And I assume yoga then is mentioned somewhere in this product listing. Yeah, yoga staple. Perfect. So that's a good set of results. You're also getting a reflection of the correct pricing as well, which is brilliant. Regular price 48 as low as 38.40. So that's in the data set. So let's ask some follow-up questions and let's see, kind of maintain the context of the conversation. What sizes does the Zeppelin come in? Okay, so there you go. It returns the correct sizes, 32 to 36, which you can see here. And let's ask a follow-up question without the context of the product name. What colors do you have? So out of context, this could be about anything. Great, so it's accurately reflecting that it has blue, green, and red, which you can see here. Here are some options for you to explore. So we have a link to that product. It is giving us more options for other yoga pants. So not exactly answering that question, but we are getting the correct answer there and we can click through. Let's ask another follow-up question. So what material is this made from? And again, it's GPT-4, so let's include typos and let's see how it responds. Okay, here's our response. And perfect, yeah, it picked up the right product, even despite such a ridiculously worded question. Fleece, Lumatex, Mandex, and wool. We can verify that there. And then that matches the product description. Okay, so let's try a complex question. So let's ask, is this product suitable for workouts? And also, if I buy it and need to return it, what's the returns window? So here we're going to need to go to the knowledge base, but we're also going to need to understand the product description. Okay, so here's the response. I accidentally left in this test message knowledge fetch, but at least we know it went to the knowledge base. It is indeed suitable for workouts, which I believe is correct. I think it's mentioned, yeah, workout pants. If you need to return it, accepts returns within 30 days of receipt, which is correct, and we know that because it was fetched from the knowledge base. Here are some other products you might find useful for your workouts. So some nice kind of upsells, cross-sells here. Finally, let's test the guardrails on this. So we'll ask an unreasonable question in the context of an e-commerce bot. So do you believe in aliens? And there you go. Yeah. While I don't have personal beliefs, I can help you with any questions about Luma's activewear or accessories. Why is the sky blue? That's an interesting answer. It is actually answering the question, which it probably shouldn't. So within the fallback response, I probably need to update the prompt to keep it much tighter than that, so it doesn't even answer that question. Great, so that's a flavor of how to implement a natural language query system within your chatbot. As you can see, it comes with its own considerations and challenges. The big one for me is refining prompts. It is a huge amount of trial and error, and then the need for a more formal evaluation framework when doing that. So as you saw in that demo, there's a lot of unstructured testing, whereas when you get into a production stage, you need to have a formal structure of questions and follow-up questions. And then as each version of the bot is rolled out in terms of updated prompts or changes to the flows, you need to be able to rerun that test suite and be able to quantifiably measure the results. Testing with real-world users is crucial, so getting this in front of a subset of customers will be invaluable and will allow you to then iterate over what types of questions actual customers are providing. As I mentioned, natural language query works well in a very well-organized, well-structured database that's not too complicated. So a lot of work may need to be done upfront to flatten out and create an index of the various content that you need accessible by the chatbot. Security and permissions management is another key challenge you're going to face. There are various prompt injection techniques that malicious actors can use to try to change the nature of the system message that the LLM uses to generate a response. This means it's possible that the query that's run against your database may be looking to drop tables, access confidential information, or generally disrupt operations. So it's crucial that you lock down the permissions at the server level so that there is only read-only access to this data. And as I mentioned, all of this data is public anyway, so if there is a data leak of this data set, it's no different to someone just reading the contents of the website. If you're using natural language query, where custom permissions and confidential information may be at risk of being exposed, then a huge amount of care is needed in designing that architecture. Within this type of system, data synchronization is going to be very important, where new products, updated products, or product deletions are accurately reflected in the dataset. So as you can see, this natural language query methodology has dramatically improved the relevancy and accuracy of the results. It can also handle complex queries and keep track of the conversational context. The responses are faster than the system built in the first video, while it is also slightly cheaper because there are less LLM calls. That being said, this system still isn't perfect. There are still refinements needed on the prompts themselves. There's a lot more testing needed, and a full evaluation framework is needed to formalize testing. Where to go next with this? I'll be interested to hear your thoughts. Drop a comment below. I'd like to test out how to answer transaction-specific queries and the permissions around that, or possibly some human-in-the-loop functionality where we can escalate to a human agent. If you found this video informative, then please give it a like, subscribe to our channel for more chatbot and AI content, and let me know in the comments what you'd like to see next. Thanks for watching.